Okay, so I started to talk about Chapter 2 a little bit last week, and I'm going to keep doing it. So, by the way, for now at least, I'm going to skip the following parts of Chapter 2, the part about adjacency matrices and the part about center and periphery. So you can, as far as I'm concerned, you can skip those at least for now. I might come back and talk about those a little bit, but not in the near future. So what I'm going to do today is build up to an important theorem. It's Theorem 2.6 in the book that it's a pretty nice characterization of bipartite graphs. We've talked about bipartite graphs already. We have talked about ways of determining whether a graph is or is not bipartite. You had to do that homework problem where you really had to think a lot about what makes a graph bipartite or not. And mostly what we looked at was if you can find a partition of a graph, if you can find the two sets such that all the edges go between one set and the other set, then it's clearly bipartite. But then if you can't do it, then how do you show that a graph is not bipartite? One way that we used was if we could find a triangle in the graph, then we know that it's not bipartite. Anyway, we're going to find a complete characterization of bipartite graphs by the end of this video. Okay, so here we go. Oops. My alarm went off. Okay, I guess it's gone. All right. Suppose we have a walk, and if you recall, a walk is just a sequence of vertices such that consecutive vertices are adjacent. So V0 and V1 are adjacent to each other, V1 and V2 are adjacent to each other, and so on. It's like you're walking from vertex to vertex, and you can only walk from one vertex to the other if they're adjacent in one step. So suppose we have such a thing, and suppose it's a walk of length at least 2, and that the first vertex and the last vertex are the same, and that there's no repeated edge. Then, right, another way of saying this is that W is non-trivial. A trivial walk would have length 0. We're saying that this has length at least 2. Also, a walk of length 1 couldn't possibly have V0 and VK be the same. Like if K is 1, then V0 is a neighbor of V1. So if you're going to end up back at V0 by the end of the walk, you have to take 2 steps. You can't just take 1 step. So anyway, we call a walk of length more than 0, we call it non-trivial. So this is a non-trivial walk. It's also closed. Closed just means that the first and last vertex are the same, meaning that at the end of the walk, you're back to where you started. And it's a trail. If you remember, a trail is just a walk that has no repeated edge. So that's what we're talking about. We're talking about a walk that is a non-trivial closed trail. And if that's the case, we call this a circuit. We call that walk a circuit. So, right. There's many ways to draw a circuit. I mean, a sort of simple way is to just make all the vertices distinct. So this could be like V0, V1, V2, V3, and then V0 would be the same as V4. So I start here, I go all the way around and I end up back where I started. But I don't want to get too crazy, but here's another circuit. V0, V1, V2, say V3, V4, V5, V6. V3 will be the same as V7. So I'm walking around and I'm like here again. This will be V8. V2 will be the same as V9. And then maybe V0 will be the same as V10. That's also a circuit. It didn't repeat any edges. It did repeat some vertices, but no edges. If we're talking about a circuit where all the vertices except for the first one and the last one are distinct, because of course the first one is the same as the last one, but if other than that all the vertices are different, then we call that a cycle. So this is called a cycle. This is a circuit that is not a cycle. Okay, so we say that a graph is connected if for any pair of vertices u and v that there's a uv path, so there's a way to get from u to v. We call a graph, let me start over. We say that a subgraph of G, when I write this, it looks like it's the same symbol that we use for subset, but this means H is a subgraph of G. And we call H a component of G if H is connected and H is not a proper subgraph of any H prime that's a subgraph of G that is also connected. So let me point to two pictures here at the bottom of the page. This one is just connected. You can check any two vertices you look at. There's a path from one to the other. Like I can look at these two and then I can say there's this path. There's also this path, but as long as there's one path from this vertex to this vertex, then we're happy. And you check every pair of vertices, but it's a small graph and it's pretty easy to look at it and convince yourself this is a connected graph. This one is not connected. I purposefully drew it in a slightly deceiving way, although it probably doesn't trick anybody too much, but I drew it so that, this edge is sort of going over this stuff. But if you think about it, for example, there's no way to get from this vertex to, say, this vertex. From this vertex, I can only reach this vertex, and from this one, I can only go back to where I started. So these two vertices are in a component by themselves. Like these two. I'm kind of tempted to draw a bubble around them, but I don't want to mess up the picture. These four vertices are in a different component. By the way, what if I were to circle these three vertices? Actually, maybe I don't want to do too much, but I'll go ahead and do it. If I circle just these three, the part that I drew a bubble around, this is a connected graph. This is like a triangle. These three make a triangle. We would not call this a component, though, because to call it a component, it has to not only be connected, but it isn't a proper subgraph of anything else that's connected. The reason why this isn't a component is because I could have drawn my bubble a bit larger and it would still be connected. In other words, I could have included this fourth vertex, and that is also connected. So to call it a component, we really require that you couldn't make the subgraph any bigger and have it stay connected. If I circle these four, that is a component, because if I try to include anything more now, the only thing more that I could include is maybe this vertex or this vertex, and if I did that, it would no longer be connected because there's no way to get from these four to either of these two. So this graph we're looking at has two components. The first component, well, like you don't really have a first component and a second component, but one of the components consists of these two vertices and the edge between them, and the other component is these four vertices and the edges among those. Okay. In a connected graph, we say the distance from U to V. Sometimes we, if it's clear what graph we're talking about, we don't write this subscript. This is a lot like when we write a subscript for a graph when we're talking about the degree of a vertex. Sometimes we write like DEG sub the name of the graph. But if we're talking about multiple graphs, or if we just feel like clarifying what graph we want to talk about, then we put the subscript there. And what this is it takes two vertices, U and V, and it tells you the minimum length of a UV path. This is just called the distance from U to V in the graph G. A UV path that has that minimum length is called a UV geodesic. And you might, a UV geodesic is not necessarily unique. Like maybe I'll just look at this graph again. Say I've got this vertex and this vertex. The distance, so the distance from V1 to V3 here would be 2, right? I can get there in 2 steps. I can go this way or this way. And the fact that I see 2 ways to do it, that means that there's 2 different geodesics here. This path has length 2. This also has length 2. Okay. So then I think I'm ready to state the big theorem that we're going to prove today. So this is Theorem 2.6 in the book, once again. I'm giving a slightly different proof. It's really basically the same proof, but it's superficially different than what appears in the book in certain ways. So, right, the statement is that G is bipartite if and only if G has no odd cycles. We have been using a limited form of this theorem when we said that if G has a triangle, then it's not bipartite, right? Because if G has a triangle is an odd length cycle. And by the way, when I say an odd cycle, I'm referring to the length of the cycle. So a triangle would be a cycle of length 3. And so if a graph has a triangle, then that counts as an odd cycle, which means it can't be bipartite. We've been using that, but we did not talk about all odd cycles, and we did not have like an if and only if statement in the past. But now that this is the theorem that we're proving. So this is an if and only if statement, and so one way to prove this is by proving each direction separately. So let's prove the forward direction. In other words, I'm about to prove that if G is bipartite, then G has no odd cycles. So suppose G is bipartite, and that means that it has a partition. Say it has partition A, B. So now let's consider a cycle. Say we have a cycle U naught up to UK. Of course, UK is the same as U naught because it's a cycle. And so suppose we have such a cycle in G. Now, these vertices, they're all either in A or in B, right? A, B is this partition. That means every vertex is either in A or in B, but not both. And all of the edges in the entire graph go from A to B. They have one end in A and the other end in B. So if we have this cycle, and keep in mind that consecutive vertices are adjacent, so U naught and U1 is an edge. So let's say U naught is in A. Just suppose that it's in A. It's either in A or in B, so for the moment, let's assume that it's in A. That means that U1 would have to be in B because every edge goes from between A and B. So if U naught and U1 are adjacent, and if this one's in A, then this one has to be in B. And then in turn, that would mean that U2 has to be in A again. And you can see how this goes. This just alternates because the next vertex in the cycle is always a neighbor of the previous vertex. It has to be in the opposite set, whether it's A or in B. The next one has to be in the opposite. So it goes A, B, A, B, A, B. So in general, U sub I is going to be an A for the even values of I, like U0, U2, U4 would all be in A. And the rest of them, the odd subscripts, U sub I is all in B. That means K has to be even, right? Because if K was odd, then U sub K would be in B, but U sub K is the same as U sub 0, and I already know that U sub 0 is in A, so U sub K can't be in B, it has to be in A, and that means that K has to be even. So we're talking about an even length cycle. Right? So, we just considered an arbitrary cycle and concluded that if U naught is in A, then the length of the cycle has to be even. By the way, if U naught was in B instead of A, then I would go through the same argument and I would just switch all the B's and A's. If U naught was in B, then, wait, where am I pointing? Yeah, if U naught was in B, then this one would be in A, and this one would be in B. And the point is that it just switches back and forth between B's and A's, and you still conclude that the length of the cycle must be even. So that's it for the forward direction. We assumed that G was bipartite, and we considered any cycle, and we showed that that cycle must have even length. In other words, G has no odd cycles. Okay, so I'm happy with that. Now let's prove the other direction. So the other direction is this way, so I'm going to assume that G has no odd cycles and then prove that G is bipartite. And this is the harder direction. So I'm breaking this down into a couple of claims. The first claim is that the components of G must be bipartite. So, in other words, if H is a component of G, then H is bipartite. So let's prove that claim. Consider a vertex in H and consider the following two sets of vertices. I've got my set U, which is the set of vertices in H that have an even distance in U. And actually, let me clarify. This is the distance in H. Right. So U is the set of vertices, or the distance in H from U to X is even. W is the rest of the vertices in H. I could have written this another way, but I didn't have too much space, so of course W would be the vertices that have an odd distance to U, but I just described it this way. This just means all the vertices in H if you subtract the vertices in U. Of course, that's just the same thing as saying the distance to little u is odd. So what are we doing with these two sets of vertices? I'm going to claim that this is a partition because I'm claiming that H is bipartite, and I've just defined these two sets of vertices, and I'm going to claim that this is an appropriate partition showing that H is bipartite. What do I have to do to show that? I just have to show that there's no edge with both ends in U, and then I have to show that there's no edge with both ends in W. That's all I have to do. So suppose, for the sake of contradiction, that I do have an edge with both ends in U. So I have V1, V2, and they're both in U, and there's an edge from V1 to V2. Then H has an odd circuit. An odd circuit consisting of, I have a picture here. So H has an odd circuit consisting of a UV1 geodesic, meaning like this is a path from U to V1 whose length is the distance from U to V1. I defined geodesic earlier. The distance from U to V1 is even because V1 is in this set U, and U is the set of vertices whose distance to the vertex little u is an even number. So this has an even length. Similarly, this path has an even length from U to V2 because V2 is in the same set. And then I have this edge, and if you put these things together, that makes a circuit whose length is odd. Now, let me explain something. I'm being careful here. We're trying to do a proof by contradiction. Let's take a step back and look at the big picture. I'm trying to show that H is bipartite. I have these two sets of vertices. I want to show that this is a suitable partition showing that the graph is bipartite. We have supposed for contradiction that I have an edge in here. And I'm going to get a contradiction if I find an odd cycle, then that's a contradiction. Right? Because I'm assuming that G has no odd cycles, and of course that means H has no odd cycles because H is a subgraph of G. So I would get a contradiction if I found an odd cycle. I have not necessarily found an odd cycle. Let's go back to this picture. The way I drew this picture, it looks like an odd cycle. I mean, it literally is an odd cycle. Just because all these vertices are distinct. However, the picture doesn't really have to look like this. Like some of the vertices on this path might be the same as some of the vertices in this path, right? Like you might have U here, V1, V2. Right? The geodesic from U to V1 and the geodesic from U to V2, they might share some vertices. Oh, I forgot to draw this edge because they're adjacent. But the point is that there's an odd circuit. Being careful about using the word circuit. So we have an odd circuit consisting of this geodesic, and this edge. What I still need is I need to find an odd cycle. So that brings us to claim 2. Claim 2 just says that every odd circuit contains an odd cycle. And that's going to be the contradiction that we need. But we have to prove claim 2. Well, take a look at this picture. This is an example of an odd circuit. I didn't number the vertices, but you can see a circuit of length 7. If I start at Z, I go around here, and that's 3 steps. I go around here, that's 4 more steps, and then I'm back at Z. So I see this odd length circuit, and it isn't a cycle itself. However, I can easily see that it does have an odd cycle, just these 3. So what is the argument in general that this works? If you have an odd circuit and Z is a repeated vertex, so the circuit goes through Z twice, then Z naturally breaks that circuit into 2 circuits, C1 and C2. Basically, you can start at Z and then go around until you hit Z the very next time. And then that, we can call that like C1. And then there's the rest. So now that we're back at Z, we keep going until the end, and we call that circuit C2. And the thing is, the length of the entire circuit C is the sum of the lengths of C1 and C2, right? This long circuit, when we put them together, had a length of 7. C1 has length 3, C2 has length 4. So the length of C1 plus the length of C2 is the length of the big circuit. And if the big circuit has odd length, then basically this just comes down to the fact that even plus even is even. So these 2 couldn't be even because then their sum would be even. So one of them must be odd. In fact, they exactly one has to be odd. The only way to get an odd number is to do even plus odd. So one of them is even and the other one is odd. Therefore, if you just look for the shortest odd circuit, then that one has to be a cycle. Another way of thinking of this is, once you find your odd circuit, you can find an odd cycle by just cutting out a repeated vertex and finding a shorter odd circuit until eventually you find a cycle. So that's the proof of claim 2, that every odd circuit contains an odd cycle. So where does that put us? Going back to the big picture, we were still proving claim 1. Claim 2 was just part of the proof of claim 1. Claim 1 is saying that if H is a component of G, and remember we're assuming that G has no odd cycles, that H is bipartite. I defined these 2 sets, U and W. I just argued by contradiction that I can't have an edge with both ends in U. Similarly, I couldn't have an edge with both ends in W, because if I did, then as we've seen, H would have an odd circuit, and then by claim 2 it would have an odd cycle, and that's a contradiction, because we're assuming that G has no odd cycles, which means that H has no odd cycles. So that's the contradiction that we need to prove claim 1. And like I was saying, you get a similar contradiction if you assume that there's an edge with both ends in W. If there was an edge with both ends in W, then I would go back to this picture and I would say, well, now this time this path would have an odd length and this path would have an odd length, but then I would have odd plus 1 would still be odd. So I would have my odd circuit, and then I would repeat the rest of the argument. So for basically the same reason why we can't have an edge with both ends in U, I also can't have an edge with both ends in W. In other words, this is indeed a valid partition that shows that H is bipartite. Where are we now? Well, we proved claim 1. Going back to the big picture, once again, claim 1 is just saying that each component of G is bipartite. We're assuming that G has no odd cycles. We need to prove that G is bipartite. So far, we just know that each component of G is bipartite. But then we can finish it off pretty easily. Now that we know that each component of G is bipartite, let's just say that the components are H sub 1 through H sub j, and say each one is bipartite, as we know. So say the partition of H sub I is maybe this set and this set. And then there's just one more line in the proof, but really you can look down at this picture. Here I have a graph consisting of 3 different components, and each component is bipartite. Basically, all I'm going to do is I'm going to say that G is bipartite because I can just take like all of these and all of these, and these 2 big bubbles that I just drew are a partition for G. More formally, G is bipartite with the partition. One side is just the union of all the U sub i's, and the other side is just all the union of all the W sub i's. And every edge in the entire graph goes from one of these to one of these. So we're done.